There is a photograph that stops time. It arrived on the 16th of May, 2025, from a telescope sitting motionless 1.5 million kilometers from Earth. And what it showed, what it proved beyond any reasonable scientific doubt, is that the universe you thought you were living inside is older, stranger, and more crowded with fire than anyone dared to predict. The light in that photograph left its source 13.53 billion years ago. The universe itself was only 280 million years old. The question isn't just how far we have seen. The question is why what we found there should not exist at all, and what it means that it does. We are about to travel to the edge of everything we can observe, and then push past it. But to understand why this discovery rewrites the first chapter of cosmic history, we need to understand what the observable universe actually is, why its boundary has always haunted astronomers, and why a telescope named after a man who once doubted his own most revolutionary idea has now delivered a result that may be too consequential for any single theory to contain. 3 questions are going to follow us through this entire journey. First, why is MOMSI 14, the most distant object ever confirmed by human science, so catastrophically bright? Second, what does its existence tell us about the speed at which the early universe built itself? And third, most unsettling of all, if the universe was already doing this at 280 million years old, what else has it been hiding from us at the very edge of time? There is a common misconception worth addressing before anything else, because it sits at the root of almost every popular misunderstanding about what JWST has done. When astronomers talk about the observable universe, they are not talking about the edge of space. They are talking about the edge of what light can physically reach us from, and those two things are profoundly, philosophically different. The universe began approximately 787 billion years ago. That number, pinned down to 3 decimal places by the European Space Agency's Planck satellite, represents the age of everything we know. In those first fractions of a second, the entire cosmos existed as an unimaginably dense, unimaginably hot plasma, a state so extreme that even light itself could not travel freely through it. Photons were born and immediately absorbed. The universe was opaque, it glowed, but it glowed the way a forge glows, from the inside, invisible to any observer that might somehow have existed outside it. This continued for approximately 380,000 years. Then, as the universe expanded and cooled, the plasma finally thinned enough for electrons and protons to combine into neutral hydrogen atoms in an event cosmologists call recombination. At that moment, the universe became transparent. Light was freed. Those first liberated photons have been travelling ever since, in every direction, through all of space, and we can still detect them today. We call them the cosmic microwave background, the CMB, and they represent an absolute hard limit on how far back in time any telescope can see. They are the wall. They are the fog before the fog lifted. No instrument built from matter and energy by creatures living in this universe will ever see through them, because before recombination there was nothing to see. Now here is where the numbers become disorienting in a way that never fully leaves you. The observable universe is defined as a sphere with us at its centre, not because we are special, not because we occupy some privileged position in space, but simply because we are the observers, and light reaching us from every direction defines our personal horizon. The radius of that sphere, accounting for how much space has expanded since that light was emitted, is approximately 46.5 billion light-years. Let that settle for a moment. The universe is 13.787 billion years old, and yet its observable radius is 46.5 billion light-years. Those numbers are not in contradiction. They are a consequence of expansion. The space those ancient photons have been travelling through has itself been stretching, carrying their point of origin further and further away from us, even as they crossed the intervening gulf. The light takes 787 billion years to arrive. The source is now 46.5 billion light-years away. The CMB sits at that wall, a wall at a current moving distance of approximately 45.7 billion light-years, glowing at a temperature of 2.725 Kelvin, barely above absolute zero, its original ferocious heat stretched by expansion into a whisper of microwave radiation that fills all of space equally in every direction. Every cosmological survey ever conducted, every galaxy ever mapped, every quasar ever detected, all of it exists inside this sphere. All of known cosmic history occupies the space between now and that wall, but the wall is not what JWST is trying to reach. What JWST is trying to reach is something earlier but different: the first light, the first stars, the first galaxies. The epoch astronomers call cosmic dawn, which occurred somewhere in the period between roughly 100 million and 500 million years after the Big Bang. A window of time that the CMB itself cannot show us, because the CMB predates stars entirely. There is an era between the CMB and the first galaxies, a period called the Cosmic Dark Ages, during which the universe was filled with neutral hydrogen gas and produced essentially no light. And then, at some point, gravity did what gravity always does. It won. Gas clouds collapsed, stars ignited. The universe lit itself up for the first time, and when it did, those first stars and galaxies began to burn through the surrounding hydrogen fog, ionizing it, clearing it, creating the transparent universe we inhabit today in a process called reionization. A question that JWST was built, fundamentally architecturally at the level of every mirror segment and every detector, to answer is this: what did those first galaxies look like? When did they appear? And how quickly did they build themselves out of the primordial dark? To reach them, Webb had to see light that has been stretched by the expansion of the universe into the infrared. Light that began its journey as ultraviolet radiation emitted by young, hot, massive stars that arrived at our detectors 1,000,000 times redder than it started. This is the science of redshift, and it is the measuring rod of deep time. When we talk about a galaxy having a redshift of Z1, we mean the universe has doubled in scale since that light was emitted. At Z2, it has tripled. At Z10, the universe was less than 1/11th its current size when that light began its journey. At Z14, 44, the confirmed redshift of MOMZ14, the galaxy at the centre of this story, the universe was a tiny fraction of its current size, barely 280 million years old, and everything we think we know about how galaxies form was already being tested to destruction. This is where the story truly begins. Not at the edge of the observable universe, but at the edge of what should have been possible, and wasn't. Before the James Webb Space Telescope launched on Christmas Day 2021, atop an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana, there was a broad consensus among cosmologists about what the early universe should look like. This consensus was not a guess, it was not speculation, it was the product of decades of increasingly sophisticated simulation, anchored in the lambda CDM model, the standard model of cosmology, which describes a universe dominated by cold dark matter and a cosmological constant, lambda, representing dark energy. Under this framework, the early universe was understood to build structure slowly and hierarchically. Small dark matter halos formed first, then merged into larger ones, dragging gas along with them. Stars formed inside those gas clouds. Galaxies assembled from those stars. It was a bottom-up process, intricate, gradual, and theoretically well constrained. The critical prediction that follows from this framework concerns the brightness of galaxies at very high redshift. The further back in time you look, under lambda CDM, the fewer large, bright galaxies you should find, because there has simply not been enough time for gravity to assemble them. A galaxy at Z10, seen when the universe was only 480 million years old, should be small, faint, rare, detectable only with heroic investments of telescope time. And a galaxy at Z14, seen when the universe was barely 280 million years old, should be, according to the most respected pre-JWST theoretical models, essentially invisible. The probability of finding a single, bright, spectroscopically confirmed galaxy at that epoch, in any realistic survey area, was so low that planning for it bordered on optimism. JWST was not designed to prove this model wrong. It was designed to test it, and it was widely assumed to confirm it, while filling in the detail at the highest redshifts where Hubble had been unable to reach. The Hubble Space Telescope's successor carried a 5 meters primary mirror composed of 18 hexagonal segments coated in a microscopically thin layer of gold. Gold chosen because it reflects infrared light with extraordinary efficiency, capturing every photon of that ancient, redshifted signal with an effectiveness that no previous instrument could match. Its 4 primary instruments were calibrated, at enormous technical effort and financial cost, a total mission cost of approximately $7 billion, precisely for the challenge of seeing the faint red embers of the first cosmic dawn. Within weeks of first light, Webb began returning data that made cosmologists go quiet, then go back to their calculations, then go quiet again. The galaxies were there. But they were not faint, they were bright, catastrophically, inexplicably, model-shatteringly bright. In the first year of JWST operations, photometric surveys that identify galaxy candidates by the characteristic way their light cuts off at certain wavelengths, like a cliff edge in the spectrum, began reporting dozens, then hundreds of candidate galaxies at redshifts above Z10. More than a dozen of the very brightest were spectroscopically confirmed, meaning their distances were established not by inference, but by direct measurement of their emission lines, the specific fingerprint of ionized gases at known wavelengths. And these confirmed galaxies were between 10 and 100 times brighter than the most optimistic pre-JWST theoretical predictions had allowed. The standard model of galaxy formation did not predict them. It could not account for them, and they kept appearing, one after another, with a reliability that ruled out statistical fluke. This situation acquired several names inside the community. Some called it the impossible galaxies problem. Others described it as a crisis at cosmic dawn. The more technically minded referred to it as an overabundance of UV luminous sources at high redshift, language that captures the measurement without quite conveying the vertigo of the result. The galaxies were not merely brighter than expected. They implied a rate of star formation in the early universe that exceeded, sometimes by orders of magnitude, what any existing model could explain. Something was happening at cosmic dawn that the lambda CDM framework, in its standard form, had not prepared us for. And here we arrive at the survey, whose name perfectly captures the uncertainty at the heart of this entire enterprise. In 2024, a team of astronomers led by Rohan Naidu of MIT's Kavli Institute and Pascal Oesch of the University of Geneva proposed a JWST spectroscopic program with a name that functioned as its own scientific question: Mirage or Miracle. The formal designation was JB Program Go 5224. Its purpose was to systematically follow up the most luminous photometric candidates in JWST's wide area legacy fields, specifically the Cosmos field in the constellation Sextans, and determine, through definitive spectroscopy, whether the excess of bright early galaxies was real or an artifact of measurement. Were these objects truly at the redshifts their colours suggested? Or were some of them nearby, dust-reddened, lower redshift imposters masquerading as ancient monsters? The program name contained its own honest acknowledgement of stakes. If the bright galaxies were real, if their redshifts held up under the scrutiny of the NIRSpec instrument, then something extraordinary was happening in the early universe, and the miracle would require an explanation. If they were mostly low redshift interlopers, then the crisis would dissolve, the standard model would breathe again, and a great deal of excitement in the community would need to be quietly retired. On the 16th of April 2025, the Mirage or Miracle team pointed JWST's NIRSpec spectrograph at a compact, luminous source in the Cosmos field that their photometric pipeline had flagged as an extraordinarily promising high redshift candidate. The source was entirely absent at wavelengths below 1.8 micrometers, invisible in blue light, invisible in green, invisible even in near-infrared bands where many high redshift galaxies still leave a faint trace. It appeared only at longer wavelengths, suggesting its light had been shifted so far into the red that it had crossed the boundary of what most previous instruments could detect. Their photometric estimate placed it at a redshift somewhere between Z14 and Z15, territory so extreme that even the most recent JWST record breaker, JWST GSZ140, had not reached it. The spectrum they obtained contained a sharp break, a cliff edge in the light, consistent with the Lyman alpha break that occurs when a galaxy's ultraviolet light is absorbed by intervening neutral hydrogen. More importantly, the spectrum also showed 5 rest ultraviolet emission lines, NIV at 1487 angstroms Luz, CIV at 1548 and 1551 angstroms, and C3 at 1907 and 1909 angstroms. These lines are the chemical signature of hot ionizing radiation from young, massive stars. They pinned the redshift with a precision of plus or minus 0.02. The galaxy was not a mirage, it was not a low redshift interloper, it was not instrument noise dressed up as a discovery. MOMZ14 had a confirmed spectroscopic redshift of Z1444. It was real, it existed 280 million years after the Big Bang, and it was not supposed to be there. But why it was not supposed to be there, and what its existence forces us to confront, is a question whose full weight takes considerably longer to appreciate. Because the problem with MOMZ14 is not simply that it is distant. The problem is what it is and what it is doing at that distance. Let us be precise about the nature of the problem. MOMZ14 has an absolute UV magnitude of MUV minus 20.2. In the language of galaxy luminosity, this places it at roughly 60% of the characteristic brightness of a typical large galaxy in the modern local universe. It is, in other words, not a faint smudge at the edge of detectability. It is a genuinely luminous source, seen at a time when the universe was only 2% of its current age. The difficulty this creates becomes clear when you understand what goes into building a bright galaxy. Brightness in the ultraviolet is, in the context of young galaxies, essentially a proxy for star formation rate. Young, massive, short-lived stars, the O-type and B-type stars, which burn at temperatures of 20,000 to 50, 0 Kelvin, radiate copiously in ultraviolet light. A galaxy that is UV bright in the early universe is a galaxy forming stars at a prodigious rate, converting gas into stellar material faster than the average, and doing so in a dense, efficient, well-organized way. To be as UV bright as MOMZ14 at redshift 44 requires a star formation rate, even accounting for the galaxy's young stellar population and low dust content, that pushes the boundaries of what the raw material available in 280 million years of cosmic history can plausibly deliver. Here is the arithmetic problem. The universe at Z1444 is young. The dark matter halos that will eventually anchor the largest galaxies are still small. Under the standard lambda CDM picture, the most massive dark matter halo that should exist at this epoch, the rarest, most extreme peak in the density field, has a mass of perhaps a few times 1010 solar masses. The baryonic material that falls into this halo, the gas that will actually form stars, represents a fraction of that total mass, roughly 1/6, giving you at most a few billion solar masses of raw stellar fuel, converting all of that gas into stars with 100% efficiency, an efficiency that is physically impossible under any known astrophysical mechanism, because feedback processes from the stars themselves blow gas out before it can fully collapse, would give you a galaxy that is still somewhat less luminous than MOMZ14. And yet MOMZ14 exists. The spectrum is unambiguous. The redshift is confirmed through 5 independent emission line detections plus the Lyman alpha break. The galaxy is there at Z1444, shining with a UV luminosity that the standard framework of structure formation struggles to accommodate. The research team, 46 scientists across institutions spanning MIT, the University of Geneva, Copenhagen's Cosmic Dawn Center, Penn State, the Harvard Center for Astrophysics, Cambridge, Princeton, Yale, and a dozen more, confronted this directly in their paper. The number density of bright galaxies at Z1415 implied by their detection, finding one such object in 350 square arc minutes of survey area, is more than 100 times larger than the pre-JWST theoretical consensus had predicted. Not twice as large, not 10 times, a factor of 182, with error bars spanning from 77 to 511 times the expected value. Every number in that range is a crisis for the standard model. This is not the first time JWST has reported an overabundance of bright early galaxies. The telescope has been delivering versions of this result since its first science observations in 2022. MOMSI 14 represents the extreme end of this trend. It is the most distant spectroscopically confirmed galaxy in the history of human observation, pushing the frontier 10 full units deeper in redshift than the previous record holder in certain survey comparisons, and extending the observational reach to a mere 280 million years after the Big Bang, a period when the universe was still navigating the transition from neutral to ionized, a transition that MOMSI 14 extraordinarily appears to be accelerating on its own. The galaxy is also tiny. Its physical size, its effective radius, is measured at approximately 74 parsecs. For reference, the entire disk of the Milky Way spans roughly 30, or parsecs. MOMSI 14 is compressed into a volume less than 1/400th that width, and yet it is pouring out ultraviolet radiation at a rate comparable to galaxies 10 times its size in the modern universe. The compactness, combined with the luminosity, tells you that the density of star formation inside MOMSI 14 is extraordinary even by the already extraordinary standards of the early universe. Stars are not forming here gradually, in quiet molecular cloud complexes scattered across a large galactic disk. They are forming in a violent, concentrated burst at a rate that has accelerated tenfold in the last 5 million years alone. An eye blink by any cosmological measure. The star formation history the team inferred is what they call a rising star formation history. In the 50 million years preceding our observation, the galaxy was building itself steadily. In the 5 million years immediately before we see it, its star formation rate jumped by a factor of 9, nearly a factor of 10 in less time than it takes the Earth to orbit the Sun 5 million times. Something triggered an extraordinary burst of star formation. What? Possibly a merger with another gas-rich halo, possibly an internal instability in the gas cloud from which it was assembled. The data cannot yet distinguish between these possibilities with certainty. But the pattern, a rapid, violent uptick in stellar activity, is one that will prove important when we examine what the galaxy is actually made of. Because this is where MOMSI 14 stops being merely a record breaker and starts being a detective story. The spectrum does not only confirm the redshift and the star formation history, it also reveals, in the relative strengths of the emission lines, something about the chemical composition of the gas inside MOMSI 14, the specific ratio of elements that its stars have so far produced, and what the spectrum shows is a chemical signature that should not be there, a signature that points, when you follow it carefully, not forward into the future of galaxy evolution, but backward, into the hearts of the oldest stars in our own Milky Way. This is the thread that pulls the entire story towards something even stranger than a record-breaking redshift. This is where a galaxy 13.53 billion light-years away begins to tell us something about where we come from. The emission lines in MOMSI 14 spectrum are not equally strong. Some lines are brighter than others, and the relative brightness of different lines is a sensitive probe of the physical conditions inside the galaxy. The temperature and density of the gas, the hardness of the radiation ionizing it, and crucially, the relative abundances of different chemical elements, nitrogen, carbon, oxygen. These are the elements whose emission lines dominate in the ultraviolet spectra of young star-forming galaxies, and their ratios encode the history of the stellar population that created them. What the Mirage or Miracle team found in MOMSI 14 spectrum is an anomalously strong nitrogen signal. The ratio of nitrogen to carbon, expressed as Nc, is greater than 1, meaning nitrogen is more abundant relative to carbon than it is in the Sun. The ratio of nitrogen to oxygen is similarly elevated above solar values. In the language of stellar nucleosynthesis, this is a signature that requires a very specific kind of stellar environment to produce, one that is not easily generated by the normal, steady-state evolution of ordinary stellar populations. To understand why this matters, you need to understand how elements are made in stars and in the explosions that end their lives. Oxygen and carbon are produced copiously in the cores of massive stars through standard nucleosynthesis channels, the CNO cycle, helium burning, carbon burning. These elements are scattered into the interstellar medium when the stars explode as supernovae, enriching the next generation of stellar material. Nitrogen is also produced through the CNO cycle, but its production is sensitive to the temperature and the mass of the stellar core in a way that makes it a tracer of specific stellar populations. In particular, very high nitrogen abundances, nitrogen to oxygen ratios far above solar, are observed in a handful of very specific astrophysical environments, the spectra of some extreme compact star-forming regions, and, critically, the chemical composition of globular clusters in the Milky Way and nearby galaxies. Globular clusters are ancient, dense stellar systems, spherical agglomerations of hundreds of thousands to millions of stars, tightly bound by gravity, orbiting the outskirts of galaxies. The oldest globular clusters in the Milky Way formed more than 13 billion years ago, making them among the oldest objects in the observable universe, and many of them display a chemical peculiarity that has puzzled astronomers for decades. A subset of their stars shows dramatically elevated nitrogen and depleted carbon and oxygen relative to what standard stellar evolution predicts. This nitrogen anomaly, sometimes called the globular cluster multiple population problem, is thought to be caused by a specific type of stellar object, a supermassive star or SMS with a mass of perhaps 10 zeros and solar masses or more, which burns at temperatures high enough to drive nucleosynthesis channels that ordinary massive stars cannot access, producing nitrogen in quantities that overwhelm the baseline carbon and oxygen abundance. These supermassive stars are not observed directly in the local universe. They are theoretical objects, inferred from the chemical signatures they leave behind. They are believed to have existed only in the densest, most extreme environments of the early universe, environments where gas densities and stellar birth rates were high enough to allow runaway mass accretion, building stellar objects of spectacular mass before stellar winds and radiation pressure could halt the growth. And they are believed to have been particularly common at cosmic dawn, during the formation of the first dense stellar clusters, before the universe had been enriched with the heavy elements that, in later epochs, would help stabilize star-forming clouds against runaway collapse. The nitrogen signature in MOMZ14 spectrum looks like this. It matches the chemical pattern associated with supermassive stars. It matches the pattern seen in the oldest globular clusters in the Milky Way, and the team's interpretation, carefully stated, properly hedged with appropriate scientific caution, is that we may be watching, in the spectrum of this galaxy 13.53 billion light-years away, the active formation of something like the protoglobular clusters that would, billions of years later, become the ancient stellar fossils orbiting the halo of our own galaxy. I find this genuinely haunting. The idea that a JWST has given us a direct window into the formation of the oldest objects in our cosmic neighbourhood, that the distant past and our local present are connected by a specific chemical thread woven in a galaxy that existed before any star in the Milky Way was born, is one of those moments in science where the usual sensation of looking outward suddenly reverses. MOMZ14 is not just the most distant object we have ever confirmed. It is, in a real sense, an ancestor, a chemical relative. The universe at 280 million years old was doing something that would leave a specific, measurable signature in the stars of our own galaxy 13 billion years later. When we read MOMZ14 spectrum, we are reading our own origins in another handwriting. But the nitrogen signature is not only interesting as a window into globular cluster formation, it is also a constraint on the timeline of chemical enrichment in the early universe, and this constraint creates its own set of problems. Nitrogen at the abundances seen in MOMZ14 cannot have been produced through slow, ordinary stellar evolution alone. You need at minimum 1 or 2 full generations of stars that form, live their lives and die in supernovae, to deliver the chemical enrichment seen in the spectrum. at Z 14.44, 280 million years after the Big Bang, you have time for perhaps one or two such generations, assuming the stars were very massive and therefore very short-lived. The chemical evolution of this galaxy has been compressed into a time span that makes normal enrichment histories implausible. The supermassive star hypothesis is one resolution. Another is that star formation began even earlier in the progenitor system, that what we are seeing is not the first burst of star formation in this structure, but a second or third generation building on chemical work already done by an earlier, undetected stellar population. The third possibility, more unsettling, is that our models of chemical enrichment in the early universe are themselves incomplete, and that the universe at cosmic dawn was processing elements faster, more efficiently, and through channels that we have not yet fully identified. There is also the matter of what MOMM Z14 is doing to its surroundings. The spectrum shows a relatively weak Lyman alpha absorption damping ring, the signature of neutral hydrogen surrounding a galaxy, which suggests that the space immediately around Z14 is at least partially ionized, despite every existing model of the epoch of reionization predicting that at Z 1444 the intergalactic medium should be essentially 100% neutral. MOMM Z14 is apparently clearing its own bubble in the primordial hydrogen fog, punching through the surrounding gas with its radiation, creating a pocket of ionized space in a universe that should, by all theoretical accounts, be completely opaque to this kind of process at such an early time. This is not a small thing. This is a galaxy rewriting the timeline of reionization, one of the most consequential physical transitions in the history of the universe, by doing it earlier than any simulation predicted. This is what is meant when scientists describe MOMM Z14 as a cosmic miracle, not a violation of physical law, not supernatural intervention, but a measurement so far outside the range of theoretical expectation that the word miracle is the honest acknowledgement that our models have failed us in a way we have not yet fully understood. Let me tell you about a specific moment in time. It is 16th April 2025. At a computer terminal somewhere connected to the Space Telescope Science Institute's data pipeline, a young postdoctoral researcher at MIT's Kavli Institute for Astrophysics and Space Research is watching data from a JWST near-spec observation unfold. His name is Rohan Naidu. He is the lead author of the paper that would eventually carry MOMM Z14 to the world, and the program whose data he is now processing, the Mirage or Miracle Survey, JWST program 5224, is one he co-designed with Pascal Oesch of the University of Geneva, explicitly to answer the most pressing question in observational cosmology. The program had been conceived out of a specific frustration that anyone who has worked at the bleeding edge of observational astronomy will recognize. For 2.5 years after JWST's first science observations, photometric surveys had been reporting an avalanche of candidate high redshift galaxies, objects that looked, from the colours of their infrared emission, as though they might be extraordinarily distant, extraordinarily luminous, and extraordinarily early. But photometric identification is not the same as confirmation. A galaxy's apparent colour can be mimicked by several different physical scenarios. A galaxy at very high redshift, with its ultraviolet light redshifted into the infrared, looks broadly similar to a galaxy at low redshift that is simply very dusty, or to a galaxy with unusual emission line properties that cause its light to drop sharply at certain wavelengths. You cannot build a revolution in cosmology on photometric candidates alone. You need spectra. You need the precise fingerprint of chemical emission lines pinning the redshift down with the precision of a measurement rather than the ambiguity of an inference. The Mirage or Miracle Survey was designed to deliver that precision systematically, at scale, for the brightest and most extreme photometric candidates in JWST's wide area fields. 5 NIRSpec pointings, 2 in the UDS field, 3 in Cosmos, each receiving 4.4 hours of integration time in prism mode, each designed around primary targets that photometric pipelines had flagged as the most promising high redshift sources in their respective fields. The survey name, chosen with deliberate clarity, was the team's honest acknowledgement that they did not know what they would find. The bright early galaxies were either a mirage, a statistical fluctuation, a systematic error in photometric selection, a population of misidentified interlopers, or they were a miracle. The data would decide. On the 16th May 2025, the spectrum of MOMZ-14 was publicly confirmed. The galaxy had first been detected photometrically, its unusual colour flagged by the automated pipeline, and then observed spectroscopically in the 16th of April run. The analysis took weeks. Emission lines had to be identified and measured. The Lyman alpha break had to be characterised and confirmed as the correct physical interpretation rather than a lower redshift Balmer break. 5 independent line detections, NIV 1487, CIV 1551, C3 1907, C3 09, had to be verified against contamination and noise. The redshift of Z 14.44 plus or minus 0.2 had to be established as robust before any of it could be announced. When it was announced, Naidu told the world through NASA's press release, "With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting." That combination of words, challenging and exciting, is, I think, one of the most carefully calibrated sentences a scientist can deliver about a result that has just made large portions of their theoretical framework obsolete. It is not the sentence of someone who is panicking. It is the sentence of someone who has spent enough time in science to understand that being wrong in a specific, measurable way is the most productive thing that can happen to a field. Behind that measured public statement lies the full texture of what it actually means to spend your professional life chasing the earliest moments of the universe. Rohan Naidu represents a generation of astronomers who grew up knowing that JWST was coming, who built their careers around the promise of infrared space astronomy at an unprecedented scale, and who have now spent several years in the extraordinary position of watching their theoretical scaffolding disassemble itself in real time, brick by brick, with each new spectroscopic confirmation. The impossible galaxies problem, as it is sometimes called, is not merely a scientific puzzle. It is a personal reckoning for everyone who spent the years before JWST's launch writing papers that confidently predicted what cosmic dawn would look like. Pascal Oesch, Naidu's co-PI on the Mirage or Miracle program, was himself part of the team that discovered GNZ11, the galaxy that first hinted, with Hubble in 2016, that something anomalous might be happening in the early universe. GNZ11 sat at a redshift of approximately Z 10.6, placing it in a universe that was about 420 million years old. Even at that redshift, it was unexpectedly bright, bright enough to raise eyebrows, bright enough to generate theoretical papers trying to explain it, isolated enough that it could still, if you were determined, be dismissed as an outlier. A single extraordinary object tells you you have found something unusual. A population of them tells you the model is wrong. Jacob Shen, a postdoctoral researcher at MIT and a member of the team, spoke to this directly. There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. Yijia Li, a graduate student at Penn State who contributed to the analysis, captured the essential feeling of working at this frontier. It's an incredibly exciting time, with Webb revealing the early universe like never before and showing us how much there still is to discover. There is a particular quality of experience that belongs exclusively to people working at the edge of what any instrument in human history has ever resolved, and JWST has created a generation of astronomers who inhabit that experience. Every spectroscopic observation at Z13 is a first. Every confirmed galaxy in that epoch is, by definition, the furthest thing humanity has ever confirmed until the next one. The record-breaking is not the point. The point is what the records reveal about the structure of the early universe. But the sensation of standing at the literal frontier of observable time is, by all accounts, unlike anything else in science. What strikes me most about the Mirage or Miracle survey's design, though, is the honesty embedded in the name. The survey was not called the Galaxy Confirmation Project or the High Redshift Spectroscopy Initiative, or any of the dozens of neutral, professional-sounding titles that could have been chosen. It was named for the uncertainty itself. The team was willing to spend JWST time, the most precious observational resource on Earth, to find out that the answer was a mirage. They were willing to discover that the photometric galaxy counts were wrong, that the candidates were interlopers, that the crisis at cosmic dawn was an artifact of measurement rather than a genuine signal. Science at its best is exactly this: the willingness to invest fully in being proven wrong, and in the event, the survey proved them right, not in the sense that their predictions were confirmed, but in the sense that the miracle was real, and the mirage was not MOMZ14, stands as a testament to that courage. It is the furthest thing ever seen. It is a cosmic miracle, and it was found by people who were genuinely prepared for it not to be. What MOMZ14 does to reionization theory is, in this author's assessment, one of the most consequential aspects of the discovery, and it has received considerably less attention in popular coverage than the redshift record itself. To understand why, you need to understand what the epoch of reionization is, why it matters, and what existing models have predicted about when and how it unfolded. The universe at early times was filled with neutral hydrogen gas, the product of the Big Bang's nucleosynthesis and the subsequent cooling of the plasma during the first 380,000 years. This neutral hydrogen is, for specific photons, ultraviolet photons with energies above 13.6 electron volts, the ionization energy of hydrogen completely opaque. When the first stars and galaxies formed, they began producing prodigious quantities of these ionizing photons, which carved out expanding bubbles of ionized gas in the surrounding neutral medium. These bubbles grew, overlapped, and eventually merged until the entire intergalactic medium had been ionized, transformed from a fog of neutral hydrogen into the transparent ionized plasma that fills intergalactic space today. This transformation is reionization. It is the last global phase transition in the history of the universe, and it marks the moment when the cosmos became for the first time transparent to starlight over large scales. The question of when reionization was completed, and more importantly, when it began, has occupied cosmologists for decades. The standard picture, built from a combination of CMB observations, studies of quasar absorption spectra, the so-called Gunn-Peterson troughs, and galaxy luminosity function measurements, places the bulk of reionization between approximately Z6 and Z10. That is, the universe became substantially transparent between about 500 million and 1 billion years after the Big Bang. Some reionization certainly began earlier. The first galaxies began punching ionized bubbles in the neutral medium as soon as they formed, but the dominant models suggested that at Z14 the universe should still be essentially completely neutral. The neutral fraction of hydrogen at Z14, under virtually every existing reionization model, is predicted to be approximately 100%. The tiny pockets of ionized gas that exist should be confined to the immediate vicinities of the most extreme earliest forming objects. If they exist at all, MOMZ14 appears to live inside one of those pockets. The weakness of the Lyman alpha damping wing in its spectrum, the signature of neutral hydrogen absorption, suggests that the galaxy's immediate surroundings are not fully neutral. Something has ionized the space around MOMZ14, and the most likely candidate is MOMZ14 itself, along with whatever cluster of early forming objects surrounds it. The galaxy is apparently powerful enough. Its ultraviolet output is intense enough. Its star formation rate is bursty and concentrated enough to have carved a bubble of ionized gas around itself in a universe that should be almost perfectly opaque. This is not entirely without precedent. Even before JWST, theoretical models had allowed for the existence of ionized bubbles around the most extreme early sources. But MOMZ14 pushes this into territory where the predictions become genuinely uncomfortable. The redshift of 44 places it 10 units in redshift beyond where the main epoch of reionization was thought to be occurring. For a single galaxy, a galaxy with a stellar mass comparable to the Small Magellanic Cloud, approximately 10 in 8 solar masses, to have already carved a detectable ionized region around itself at this epoch, implies either that the galaxy has been producing ionizing radiation for longer than its apparent youth should allow, or that the efficiency with which its radiation escapes into the surrounding medium is far higher than standard models of galactic interstellar media would predict. There is a clue in the spectrum. The UV slope of MOMZ14's continuum, the rate at which its brightness changes with wavelength, parameterized as beta, is measured at -2.5. This is an extremely steep blue slope. In the physical language of stellar populations, a steep negative UV slope means the galaxy's light is dominated by the hottest, youngest, most massive stars, with minimal reddening by dust. The interstellar medium of MOMZ14 is, to a first approximation, essentially transparent. The galaxy's starlight escapes into the surrounding space with minimal absorption. This is called a high escape fraction of ionizing photons, and it is exactly what you need if a single compact galaxy is to ionize a significant bubble in the surrounding intergalactic medium. In the modern universe, the escape fraction of ionizing photons from typical galaxies is a few percent. Most of the ultraviolet radiation from stars is absorbed by dust and gas within the galaxy before it can escape to ionize the intergalactic medium. MOMZ14 appears to have nearly no dust. Its UV slope and the absence of strong dust emission signatures both point to a largely dust-free system. This is consistent with the expectation that very early galaxies, before many generations of stellar evolution, have had time to produce the heavy elements that condense into dust grains, should be cleaner, more transparent environments than their modern descendants. And if this is true, if MOMZ14's escape fraction is dramatically higher than modern galaxies, then it and systems like it may have contributed substantially more to the reionization of the universe than their total stellar mass alone would suggest. There is a second, more systemic implication. If a single galaxy at Z1444 has already begun locally reionizing its surroundings, and if the number density of such bright, UV luminous galaxies at this epoch is more than 100 times higher than theoretical models predicted, then the timeline of reionization may need to be substantially revised. Reionization may have begun earlier, may have been driven in its first phase by a population of compact, dust-free, intensely star-forming galaxies that the standard lambda CDM model failed to predict, and may have proceeded faster than the smooth, gradual process that most models have described. The JWST discoveries, taken collectively, push toward a picture in which cosmic dawn was more violent, more punctuated, and more chemically complex than the standard model's serene hierarchical assembly would suggest. The reionization timeline problem is, in this sense, a second crisis layered beneath the more publicized galaxy overabundance problem. It is not only that there are more bright galaxies at early times than expected, it is that those galaxies appear to have been more effective at transforming the universe around them than any model predicted. The history of the universe's transition from opaque to transparent, one of the most fundamental physical events in cosmic history, may need to be rewritten, pushed back in time, accelerated in its early phases, and attributed to a population of sources that nobody knew was there. This raises questions that cut to the heart of how we construct cosmological models in the first place. The lambda CDM framework is not wrong in any simple sense. It successfully accounts for an enormous range of observations, from the power spectrum of the CMB to the large-scale structure of the universe at late times to the statistics of galaxy clusters and voids. But something in its prescription for early galaxy formation is producing predictions that are quantitatively, systematically wrong by factors of 100 or more. The question is where, specifically, the model has gone wrong, and here, the scientific community is genuinely, productively divided. There is a tempting narrative, common in popular science coverage, in which JWST's discoveries constitute a flat refutation of the standard cosmological model, a demonstration that the lambda CDM framework is broken, that the Big Bang is in doubt. that everything physics thought it knew about the early universe must be discarded. This narrative is not only wrong, it is the opposite of the situation. Understanding why requires engaging seriously with what the overabundance of bright early galaxies actually proves and what it does not prove, because the answer is more nuanced, more contested, and ultimately more scientifically productive than any simple story of a model overthrown. The Lambda CDM model rests on a set of confirmed physical observations that JWST's discoveries do not touch. The expansion of the universe is real, confirmed by every distance measure, every supernova survey, every redshift measurement ever made. The Big Bang is real. Its predictions of the abundances of light elements, hydrogen, helium, deuterium, and lithium, produced in the first 3 minutes of cosmic history, match observations at the level of 1 part in 100,000. The CMB is real. Its temperature anisotropies, its polarization pattern, its acoustic peaks, its spectral index, all accord with the predictions of an inflationary Big Bang universe with extraordinary precision. The large-scale structure of the universe, the cosmic web of filaments, voids, and galaxy clusters, matches the predictions of cold dark matter models on scales above roughly 10 megaparsecs with compelling accuracy. None of this is threatened by MOMZ-14. What is threatened, what is genuinely under pressure, is the subgrid physics of galaxy formation models, the specific mechanisms by which gas cools, collapses, and forms stars inside dark matter halos, the efficiency of stellar feedback, the process by which supernovae and stellar winds heat the surrounding gas and suppress further star formation, the escape fraction of ionizing photons, the role of active galactic nuclei and their feedback on the gas reservoirs of early galaxies. These are the inputs that cosmological simulations must specify, and they are not derived from fundamental physics. They are calibrated, semi-empirical prescriptions derived from observations of galaxies in the relatively recent universe and extrapolated backward in time. Several explanations for the excess of bright early galaxies have been proposed, and each carries genuine physical motivation. The first and most discussed is reduced stellar feedback efficiency at high redshift. In the modern universe, massive stars form, burn brightly, and die in supernovae that inject energy into the surrounding gas, heating it, dispersing it, and suppressing further star formation. This feedback loop keeps star formation rates relatively modest in most galaxies. The argument is that in the early universe, at high redshift, the conditions, gas density, metallicity, the dynamical state of the host halo, may have allowed the feedback loop to be substantially less efficient. If gas could cool and collapse faster than stellar feedback could disrupt it, then early galaxies could have converted their gas into stars at efficiencies approaching 20 or even 30%, 2 to 3 times higher than the 5 to 10% typical in the present-day universe. This alone, applied across the population of high redshift halos, could explain a factor of 10 to 20 in the excess UV luminosity function. The second explanation involves stochasticity, the idea that star formation in early, low-mass galaxies is inherently bursty and variable rather than smooth and continuous. In this picture, early galaxies undergo episodes of intense star formation followed by periods of quiescence, and our observations happen to catch a disproportionate fraction of them during their bright, active phases, creating a statistical excess of UV luminous sources that does not necessarily imply a systematically different physics, only a different distribution of activity at a given time. The MOMZ-14 data is consistent with this. The galaxy shows a tenfold increase in star formation rate in its most recent 5 million years compared to the preceding 50 million, which is exactly the signature of a bursty star formation history. The third explanation, more radical and correspondingly more contested, is that the UV luminosity of early galaxies is being boosted not by star formation alone, but by active galactic nuclei. Supermassive black holes, accreting gas at high rates, can produce prodigious UV and X-ray radiation, and if the black holes in early galaxies are more massive, relative to their host galaxy's stellar mass, than in nearby galaxies, then the AGN contribution to the UV luminosity function could be substantially larger than assumed. JWST has found several candidate AGN at very high redshift, and some of the most extreme early galaxies, including GNZ11, where near-spec spectroscopy revealed the specific emission line ratios of AGN-heated gas, appear to contain accreting black holes that are massive relative to their hosts. The MOM-Z14 spectrum does not show strong AGN signatures. The team notes that the compactness of the source is resolved rather than point-like, and the emission line ratios are more consistent with star formation than AGN activity, but this does not rule out a contribution. The supermassive stars hypothesis, after all, occupies a peculiar middle ground between stellar and AGN physics, objects so massive that they blur the distinction between the densest stellar cluster and the most primitive black hole seed. The fourth explanation, the one with the most far-reaching implications for cosmology, is that the dark matter halo mass function at very high redshift is itself different from lambda CDM predictions, that dark matter is not cold and collisionless in the way the standard model assumes, but that its behaviour at early times, perhaps through self-interactions or wave-like quantum effects at small scales, creates halo structures that collapse more rapidly, more efficiently, or in different configurations than the standard model predicts. This explanation, if correct, would not merely require adjustments to the subgrid physics of simulations. It would require a modification to the fundamental description of dark matter itself. These explanations are not mutually exclusive. Multiple effects may be operating simultaneously: reduced feedback efficiency, bursty star formation, AGN contributions, and modified halo growth rates may all be contributing to the observed UV excess at different epochs and in different populations. The challenge for theorists is to construct a model that can accommodate the JWST data without sacrificing the considerable predictive successes of lambda CDM at other scales and epochs. This is hard, it is genuinely hard, and the honest admission of that difficulty is, I think, one of the most productive scientific situations you can find yourself in. There is also the Hubble tension to consider, a separate but potentially related crisis in the standard model. The Hubble constant, which measures the current rate of expansion of the universe, has been measured with increasing precision over the past decade, and two fundamentally different methods, one based on the CMB and the early universe, one based on the local distance ladder calibrated through Cepheid variable stars and Type Ia supernovae, give results that disagree at the level of approximately 9%. A universe expanding at 67, 4 km per second per megaparsec, as Planck's CMB measurement implies, is distinctly different from a universe expanding at 73 km per second per megaparsec, as some local measurements suggest. The discrepancy has been sharpened, not resolved, by several years of JWST data, though the situation remains technically contested, with some analyses finding evidence for systematic errors in the local distance ladder and others finding none. What is clear is that if the Hubble tension is real, if it represents a genuine failure of the standard model rather than a measurement artifact, then the cosmological parameters we use to convert redshifts into ages and distances may themselves be subtly wrong, with consequences that ripple through every aspect of high redshift galaxy science. The MOM-Z14 paper adopts the Planck 2018 cosmological parameters throughout. The redshift of Z14.44 corresponds to a look-back time of 53 billion years, and to a current proper distance of 33.8 billion light-years. If the Hubble constant is higher than Planck implies, these numbers shift slightly. The galaxy is a little closer in proper distance, a little younger in look-back time, but the qualitative picture remains the same. MOM-Z14 is a galaxy that existed in the first 2% of the universe's current age, and its properties are wildly inconsistent with the standard model's predictions for that epoch, regardless of which value of the Hubble constant you prefer. The Hubble tension does, however, connect to a deeper question that MOM-Z14 brings into focus: the possibility that our standard cosmological model is not merely incomplete in its subgrid physics, but incomplete at the level of its fundamental parameters. If dark energy does not behave as a simple cosmological constant, if it evolves with time, as some recent data from the Dark Energy Spectroscopic Instrument and the Dark Energy Survey have tentatively suggested, then the expansion history of the universe was different from what the standard model assumes, and the ages corresponding to given redshifts are different, and the whole timeline of galaxy formation needs to be recalculated from scratch. This is not a likely outcome. The evidence for a simple cosmological constant remains stronger than the evidence against it. But MOM Z14 is a data point that demands we keep the question open, because a galaxy at Z14, 44 that is this bright, is exactly the kind of object that tests not just galaxy formation physics, but the cosmological framework inside which galaxy formation physics operates. There is one additional complication, one that the Mirage or Miracle paper itself acknowledges with characteristic precision, which is that the number density of bright galaxies at Z14 to 15 implied by MOM Z14 detection is based on a single object in 350 square arc-minutes. This is an extraordinarily small statistical sample on which to base a factor of 182 excess relative to theoretical predictions. The uncertainty bars on that factor of 182 are enormous. The 84th percentile of the statistical uncertainty reaches a factor of 5 on 11. Finding one very rare object in a small survey area is exactly what you would expect from random statistical fluctuation, even if the underlying number density were lower. The team is fully aware of this. The survey is ongoing. More detections, or the absence of more detections, in wider area follow-up observations will progressively tighten the constraints. The Nancy Grace Roman Space Telescope, expected to survey areas thousands of times larger than current JWST programs, is positioned to deliver the definitive statistical answer. What MOM Z14 proves with certainty is that galaxies of this brightness can exist at Z1444. It does not yet prove with statistical certainty that they exist in the numbers implied by a single detection. The theoretical expectation for this epoch was zero bright confirmed galaxies at Z14 in any realistic survey, and the observation is 1. 1 is infinitely more than 0, and the theoretical models must contend with that. OBZ14 will not hold its record indefinitely. It is in the nature of this field, in the nature of JWST itself, that every record set is a record waiting to be broken. The telescope is still early in its designed lifetime of 20 years, carrying fuel reserves that may sustain it even beyond that, and the Mirage or Miracle survey is one of dozens of programs systematically probing the highest redshifts across an ever-expanding footprint of infrared imaging. The question is not whether a more distant galaxy will be found. The question is when, and what it will tell us when it arrives. The current record stands at Z14.44, corresponding to a universe that was 280 million years old. The theoretical maximum observable redshift, set not by telescope capability but by physics, is the redshift of the CMB itself, approximately Z1100, when the universe was 380,000 years old. Everything between 14, 44 and Z1100 is in principle accessible to photons. The universe was already transparent to light below certain wavelengths in that range. But in practice, the galaxies that formed in the first 200 to 300 million years after the Big Bang, the true first generation of stellar systems, the cosmic dawn in its earliest phase, may be extraordinarily faint, extraordinarily compact, and surrounded by neutral hydrogen that absorbs their ultraviolet light before it can travel any meaningful distance. Reaching them requires not just sensitivity, but a specific alignment of circumstances, a galaxy that is bright enough to be detected, located in a region where the surrounding neutral medium has been cleared sufficiently to allow its light to pass, and observed in a JWST pointing deep enough and wide enough to catch it. The Nancy Grace Roman Space Telescope is the next major instrument in this story. With a field of view approximately 100 times larger than JWST's NIRCam, while maintaining a comparable spatial resolution, Roman is designed to conduct the wide-area infrared surveys that will transform our statistical understanding of the early universe from the current handful of confirmed high redshift galaxies into a sample of thousands. Where JWST has mapped small, exquisitely deep patches of sky and found extraordinary objects, Roman will map vast tracts of the infrared sky and deliver the population statistics, the luminosity functions, the spatial clustering, the number densities, that distinguish between the competing theoretical explanations for what JWST has found. Roman will tell us how many MOMZ-14s there are, and that number, whatever it turns out to be, will do more to constrain the physics of early galaxy formation than any single spectacular object can. In parallel, JWST's own programs will continue to push deeper and earlier. The JWST survey, the Cosmos Web survey, and the Mirage or Miracle program itself are all ongoing, accumulating data across multiple sight lines into the early universe. Statistical fluctuations, the uncertainty inherent in small number detections like MOMZ-14, will be averaged away as the sample grows. The factor of 182 excess in the galaxy number density, if it holds up, will graduate from a striking anomaly to a measured fact that theoretical models must account for without exception. If it shrinks, if the wider survey finds fewer bright galaxies at Z14 than MOMZ-14's detection implied, that too is scientifically productive. It means that MOMZ-14 is genuinely exceptional, a statistical extreme in the distribution of early galaxy formation, and the excess at lower redshifts is real but less severe than the most alarming interpretation suggests. The theoretical response to JWST's discoveries is already well underway, and this is where the science is now moving fastest. Several research groups have developed models that can accommodate the observed excess of bright early galaxies within a broadly lambda CDM framework by adjusting the subgrid physics. The most successful of these invoke some combination of bursty star formation, reduced dust attenuation, reduced feedback efficiency, and AGN contributions, layering modifications on top of the standard framework rather than replacing it. Others are exploring more radical alternatives, warm dark matter models, self-interacting dark matter models in which dark energy evolves differently in the early universe. None of these alternatives has yet achieved the comprehensive success of the standard model, which correctly predicts a vast range of observations from the CMB power spectrum to galaxy clustering at large scales to the observed properties of galaxy clusters. The standard model will not be easily displaced, but MOMZ-14 and its contemporaries have established, beyond any reasonable doubt, that something in the model's prescription for early galaxy formation is quantitatively wrong, and the work of identifying and correcting that something is one of the most active frontiers in all of physics. There is also the matter of what comes after the galaxy, the period before MOMZ-14, when the first stars were forming out of pristine gas clouds with no heavy elements at all, no carbon, no nitrogen, no oxygen. These population 3 stars, the true first generation, have never been directly detected. They are predicted to be extraordinarily massive, perhaps 100 to 1,000 solar masses, hot enough to produce copious ionizing radiation, and short-lived enough to have already died before MOMZ-14 formed the stellar population we observe. Their nucleosynthetic products, the first heavy elements they scattered into the universe through supernovae, are the chemical foundation on which MOMZ-14 was built. Detecting the direct signature of population 3 stars remains one of the great unsolved goals of observational cosmology. JWST is theoretically capable of detecting certain signatures associated with population 3 stellar populations in gravitationally lensed early galaxies. Unusually strong helium lines, extremely hard ionizing spectra, the absence of heavy element emission features. No confirmed population 3 signature has been found, but with every new spectroscopic record set by MOMZ-14 and its predecessors, we get one step closer to the epoch where they must have lived. Beyond the observational program, MOMZ-14 has opened a specific question about the formation of globular clusters and their chemical progenitor environments. If what we are seeing in MOMZ-14's spectrum is protoglobular cluster formation, the dense stellar nurseries from which the ancient globular clusters in our galaxy's halo ultimately descended. Then we have, for the first time, a direct observational window into that process at the epoch when it was actually occurring. Following up with deeper spectroscopy, resolving the spatial structure of MOM-Z14 star-forming regions, and searching for the specific chemical gradients that would confirm the supermassive star hypothesis. These are programs that will occupy JWST for years to come, and that carry implications for our understanding not just of the early universe but of the oldest structures in the Milky Way. What I find most compelling about this moment in cosmology is not any single discovery, not even the record-setting redshift of MOM-Z14. It is the texture of the uncertainty that surrounds it. We have an instrument of extraordinary capability, delivering data of extraordinary quality, showing us an early universe that is extraordinary in its departure from what we expected. And we do not yet know why. We have candidate explanations. We have theoretical frameworks being stretched to accommodate the data. We have a community of thousands of astronomers, theorists, instrumentalists, and computational scientists working simultaneously on pieces of a puzzle whose final shape nobody has yet glimpsed. This is science at its most raw, most honest, and most productive state, not a field delivering confirmed answers, but a field that has been given the data to finally ask the right questions. The James Webb Space Telescope was built to do exactly this, not to confirm what we knew, not to colour in a map already drawn, but to go to the places on the map marked with the old cartographer's phrase for the unknown, and to find out whether the monsters were real. So far, they are, and they are stranger and older and brighter than anything the standard theory predicted. Light is patient in a way that nothing else in the universe is. The photons that built the spectrum of MOM-Z14, the specific quanta of electromagnetic energy that lit up JWST's NIRSpec detector on the 16th of April 2025, triggering a cascade of analysis that would end with Rohan Naidu writing the words "a cosmic miracle" in the title of a scientific paper. Those photons began their journey 13.53 billion years ago, inside a galaxy so dense and so furiously star-forming that it was burning through its gas supply at rates that no simulation had accounted for, clearing a bubble in the surrounding fog of the primordial universe, forging chemical elements in conditions that would leave a specific signature in the oldest stars in our own galaxy billions of years later. Those photons crossed the expanding void. They reddened as they travelled, their wavelengths stretching with the growing scale of the universe, until they arrived not as ultraviolet radiation, the light of hot young stars, but as near-infrared signals at 1.8 micrometers and beyond, detectable only by a telescope coated in gold, cooled to 50 Kelvin, and positioned 1.5 million kilometers from Earth, in the shadow of a sunshield the size of a tennis court. They waited, in the most literal sense that it is possible to wait, for the universe to produce a civilization capable of building an instrument capable of receiving them. And then they arrived. There is something in this that resists purely technical description. The fact that the universe spent 13.53 billion years delivering a message about its own youth. That the early cosmos was in some sense writing its autobiography in light that only reached its reader billions of years after the fact, suggests a relationship between time, observation, and meaning that physicists are not typically employed to discuss, but which nobody who has sat with this discovery for any length of time can entirely avoid. We are the generation that received this message. We did not build the instrument that captured it easily. JWST cost $7 billion, absorbed 25 years of engineering effort across 3 space agencies, and more than 1,000 companies and institutions, survived a cost overrun that nearly cancelled it, a launch delay measured in decades, a deployment sequence so complex that 344 individual mechanisms had to succeed in sequence without a single failure. It almost did not exist. The universe came within a congressional vote of remaining unread at its earliest edges. But the instrument survived and launched on the 25 December 2021 and arrived at its orbital home at the second Lagrange point, and unfolded its golden mirror, and pointed, eventually, at a tiny smudge in the constellation Sextans that would prove to be the oldest confirmed thing humanity has ever seen. MOMZ14 is 240 light-years wide. Its mass is approximately 100 million solar masses, the same as the Small Magellanic Cloud, a satellite galaxy of the Milky Way that you can see from the southern hemisphere with the naked eye. But MOMZ14 existed at Z1444 in a universe 280 million years old, shining with the UV intensity of a galaxy 3 times its mass in the modern cosmos. It should not have been there, it should not have been that bright, and it is wearing a chemical fingerprint that may connect it, through the long arc of stellar evolution and galactic archaeology, to the oldest stars in our own galaxy's halo. Fossils of cosmic dawn embedded in our own backyard, recognizable now because we have seen the forge in which they were made. What we do not know is larger than what we do. We do not know whether MOMZ14 is genuinely representative of a population of 100 times more numerous bright early galaxies, or whether it is, in part, a statistical fluctuation, an extreme object caught in a small survey. We do not know whether the overabundance of bright early galaxies requires a revision to the subgrid physics of galaxy formation simulations, or to the nature of dark matter itself, or to the behaviour of dark energy in the early universe, or to some combination of all three. We do not know whether the supermassive stars whose existence is implied by MOMZ14's nitrogen signature will ever be directly observed, or whether, by their nature as extraordinarily short-lived objects in the most extreme environments of the early cosmos, they have already left only chemical echoes behind. We do not know where the next record will fall, what redshift the next confirmed galaxy will carry, how much closer to the Big Bang the next spectrum will reach, and we do not know, yet, what lives beyond MOMZ14 in the gap between it and the CMB. The zone between Z1444 and Z1100, between 280 million years after the Big Bang and 380,000 years after, where the first stars burned and the first chemical elements were scattered, and the story that eventually produced us was already quietly being written. That gap is still dark. JWST may reach into it, catching the signatures of population 3 stars in a lensed galaxy, or finding a spectrum at Z15 or Z16 that pushes the frontier further still. Roman may find the statistical population that turns the miracle into a pattern. Future instruments, cooler, larger, launched into a universe we understand a little better because of what Webb has taught us, may close the gap further. But the darkness beyond MOMZ14 is not empty. It is full of things we cannot yet see, things that were already happening, already shaping the universe. Before MOMZ14's progenitor clouds had collapsed, before the supermassive stars that enriched its interstellar medium were born, before the first photon was freed by the first hydrogen atom, the universe was already ancient by the time MOMZ14 stars first switched on, and we are just now beginning to learn what it was doing in those first, invisible moments. Science doesn't give us endings. It gives us the next question. And right now, the next question is the most beautiful one our species has ever been equipped to ask. What was the universe doing before the oldest thing we have ever seen? The answer is out there. It has been travelling toward us for 13.8 billion years. We are building the instruments to receive it. That is enough reason to keep looking.